Welcome once again to another exciting lesson where we are going to talk about cache mapping techniques. Alright, so the idea of uh, cache mapping techniques is to determine how blocks of the main memory are placed into lines of the cache. Now, the main goal is to reduce the access time and also increase the hit rate, as we talked about in the cache memory presentation. Alright, now the cache memory techniques we are going to be looking at are the direct mapping, fully associative mapping, and then the set associative mapping. So without wasting much time, let's go into it. Alright, so what is direct mapping? Direct mapping is the simplest type of cache mapping. So in this method, each block of main memory is assigned to exactly one cache line. Now think of it like a one-to-one link between a memory block and a specific cache line, right, which is determined using a mathematical formula, which is usually a modulo operation, right. So this approach is very efficient in terms of speed and hardware simplicity. It can suffer from a problem known as cache thrashing, right, which we'll talk about shortly. All right. So how does direct mapping work? So here's how it works step by step. So the main memory is first divided into blocks. The cache is divided into lines, and each line can hold one memory block. So each block in memory maps to one specific cache line using the formula cache line number is equals to memory block number modulo the number of cache lines. Right, so when the CPU accesses memory, the address is broken into three parts, which is the tag part, the index part, and then the offset part. So the tag part identifies the specific block from a group which would map to the same cache line. The index determines the exact cache line the block maps to, and then the offset selects the byte within the block. Right. So let's look at the cache access process. Let's break down the cache access process. So when the CPU wants to read data, the process goes like this. So it uses the index from the memory address to go directly to the corresponding cache line. After that, it checks the tag stored in that line against the tag in the address. Now if they match, it's a cache hit and the data is retrieved using the offset. If they don't match, then it's a cache miss and the data is fetched from the main memory and then placed into the cache line and the tag is updated. Right. So let's look at the structure of the main memory address, right. So let's break it down with a real example. So let's take an example where the main memory size is 64 kilobyte or 2 to the power 16 byte, and a cache size of 4 kilobyte or 2 to the power 12 byte, and a block size of 32 byte or 2 to the power 5 bytes. So now we need the number of cache lines and then we need the number of memory blocks. So to get the number of cache lines, what we do is we divide the cache size by the block size, which is equal to the line size, because the block size of the memory is equal to the line size of the cache, right. So to get a number of cache lines, we just divide the cache size by the block size, which will be 4096 over 32, giving us 128 lines or 2 to the power 7 lines. And then to get a number of memory blocks, we simply divide the memory size by the block size, giving us 2048 blocks. Alright, so in this particular scenario, because the main memory size is 64 kilobyte, which is 2 to the power 16 bytes, our main memory address will be a 16-bit memory address. So this 16-bit memory address will be now divided into three parts, right. So the offset, which is usually gotten from the block size, right. So we said the block size is 2 to the power 5 bytes, so we just take the exponent of the 2 from the block size and then use it as our offset. So our offset gives us 5 bits, and we use the offset to select the byte within a block. Alright, then the index, we get a index bit from the cache lines, the number of cache lines, right? So remember how we got a number of cache lines. We divided the cache size by the line size, which is equal to the block size, right? And it gave us 2 to the power 7. So we take the exponent and then we use it as our index bit. So the index will contain 7 bits, right? And we use it to select a cache line. And then finally, because the memory address is made up of tag, index, and offset, we can simply subtract the index and offset from the 16 bits or the memory address, and then that will give us the tag uh, bit, right? So that will be 16 minus 7 minus 5, which is equal to 4 bits, and we use the tag bit to identify the block, right? So this is how the 16-bit address will be arranged. So assuming we have 0 to 15, right? 0 to 15 bits, making up the 16 bits, right? Then the tag bit will start from the 15 to 12. So from bit 15 to 12 is our tag bit, which is 4 bits, and then from bit 11 to 5, uh, which is our index bit, 7 bits, and then our offset bit will be from bit 4 to 0, which is simply 5 bits, right? So basically, that is how the direct mapping is. All right, what are the advantages of direct mapping? Now, these techniques offer several key advantages. For one, the simplicity, right? So it is very easy to implement with minimal hardware logic. Also, since each memory block has only one possible cache line, access is very quick, and then it requires fewer comparisons. Therefore, it uses a simpler hardware, and also there is lower power consumption, right? Now, the simplicity also introduces some drawbacks, right? Which is the cache thrashing. So what is cache thrashing? Cache thrashing is actually a performance problem that occurs when multiple memory blocks repeatedly overwrite each other in the same cache line. Right? So in direct mapping, this happens when two or more memory blocks map to the same cache index. Right? Since each cache line can hold only one block, accessing these blocks in quick succession causes continuous replacement, resulting in a high miss rate. Think of it like a small box with just one slot where you keep your keys. Now, if you have two different keychains and both must go into the same slot every time you swap keys, you must remove one to fit the other, right? So that back and forth creates inefficiency and delays, which is similar to the cache thrashing in direct mapping, right? Another disadvantage is the limited flexibility, right? Where a memory block can only be placed in one specific line, which means there's no room to manage conflict. And then also, it usually has a lower hit rate or a higher miss rate, right? So compared to other mapping techniques like the fully associative or the set associative mapping, direct mapping usually results in more cache misses due to this conflict, right? So let's apply this with a step-by-step example, right? So if we have a main memory size of 64 kilobytes, which is 2 to the power 16 bytes, a cache size of 4 kilobytes, which is 2 to the power 12 bytes, and a block size of 32 bytes, which is simply 2 to the power 5 bytes, then remember how to get a cache line, right? So we just have to divide the cache size by the block size, which will give us 1 to 8 lines, which is 2 to the power 7. And then the memory blocks is the memory size divided by the block size, which will give us 2048 blocks. Now consider two addresses. Let's say address 0x1234 and then address 0x2234. Now both of these addresses share the same index, right? Because the memory block number modulo 128 is the same for both. Okay, so they map to the same cache line even though their tags are different. Now this is what leads to the cache thrashing. Now if you access one, the this is what leads to the cache thrashing, right? So if we access one of them, then the other, right? They keep evicting each other. So if we access one, then the other, then one, then the other, they'll keep evicting each other from the same line, leading to the constant misses. Right. So in summary, direct mapping is a fast, simple, and cost-effective cache strategy. However, its one-to-one mapping rule can cause conflict misses or cache slashing, right? Especially when multiple frequently used blocks compete for the same cache line. Now, while effective for mini workloads, it's often outperformed by more flexible techniques like the set associative mapping, especially in systems where the hit rate is very pushy. Right, thank you. This brings us to the end of our lesson on direct mapping. Thank you for your time. The next mapping technique we'll be looking at is the fully associative mapping.